Okay, good morning, everybody. Before we get started on math today, I wanted to sort of update you on what the schedule is going to look like for the rest of the semester. So basically, the way the book does some things goes very against my nature, and I couldn't overcome that difference for this section here. It's just all wrong. So I wound up rearranging some of these lessons. So I'll kind of edit and see what we did. We did 5.1 and then 5.2 and 6.2, and then we did 5.3. Today we're doing 6.3. Tomorrow we will do 5.4, or on Monday, and then we will do 5.5, and then we will do 6.6, and then question mark for those last days, because it turns out I somehow managed to get myself a day ahead of schedule, which is great. That just means that we have a little bit more time to spend on substitution later on. And then let's see. On Friday, November 13th, that's like 2 weeks from today, we will have a review, and then the following Monday will be your last exam before the final. And then we will come back. Well, we won't come back, but oh yeah, we will come back that week. So this, what is this? Okay, so this would be the week before Thanksgiving. We'll do 5.6 and 6.4. And then that Monday, again, is a question mark. I'm not sure if I'm going to make that a remote day or what. But then after Thanksgiving break, we just have one like review day, and then it's dead week, and then it's time for our final. Any questions about the schedule? Just figured I would update you because I'm going all out of whack for this chapter, or these two chapters. All right. In that case, let's jump in on the warm-up problem. For 6.3, we want to find some antiderivatives. Okay, I suppose I should mention before we start, when we say the most general antiderivative, it should be of the form f of x plus c. Okay, so just write that c out back to make sure that we are classifying a class of functions or a family of functions for which each of them would be an antiderivative of each of these functions. All right, let's have a show of hands. Raise your hand if you're finished with all the warm-up problems. Or two or more warm-up problems. Okay, take another minute or so. All right, let's give these a shot. So how are we going to do this first one? We want to find the antiderivative of 2x cubed plus 3x squared minus 7x plus 1. Let's handle each piece one at a time, because we know that for finding indefinite integrals, we have the rule that the integral of a sum of functions is equal to the sum of the integrals of those functions. So if we want to find the antiderivative, we can treat each piece individually. So let's start with 2x cubed. Who can help me do the antiderivative? Kevin?
1/2 x to the 4th.
Yeah, 1/2 x to the 4th. So how did you do that? We somehow got from here to x to the 4th over 2. What happened?
I just realized that the exponent would have to go up 1, and then I figured what would the coefficient be if it got to 2 with an exponent of 4.
Yeah. So for those of you at home, Kevin was explaining, we should raise the power by 1. And since we're doing the opposite process of taking a derivative, when we do the derivative, we multiply down the old power and we subtract the power by 1. If we want to do the opposite of that, we should add 1 to the power and divide by the new power. So we get x, the 2 floats, and then we get x to the 4th, and then we should divide by the new power, which is 4. So we get 2 over 4 x to the 4th and get x to the 4th over 2. Okay, I'm going to do the rest of this fairly quickly. 3x squared, that's going to become x cubed. We raised the power by 1 and divided by 3. Since there was a 3 out front, I canceled those terms. Minus 7/2 x squared plus x. All right, am I all done? Heads are shaking. Why? Why am I not done? Emma, you know? Oh, not raising your hand. Mia?
Plus c.
Plus c. Yeah, we should have plus c for some constant. Okay? Any number we put in there, doesn't matter what it is. If we take its derivative, it's going to go away. So we should put it in here just for completeness sake. All right, next one. How should I handle this first term? 2 over x. What's that antiderivative? Alice?
It's going to be 2 ln.
Very good. It will be 2 ln. Anything in particular that I need to do here?
Absolute value.
Absolute value. Yeah, very good. All right, and then what do I do with this term? 4 over x squared. should I find that antiderivative? Is it going to be 4 ln of x squared plus c? Agree or disagree? Looks plausible. It's plausible, but it's actually not quite right. Okay. The rule we learned for ln was that ln x is the antiderivative of 1 over x. The other rule we learned was that x to the n plus 1 over n plus 1 is the antiderivative of x to the n whenever n is not equal to -1. If n's equal to -1, then we have 1 over x, and that's when ln x is the antiderivative. So we had these two rules, the Lnx rule and this rule, and unfortunately the second one here is going to fall underneath the second rule, okay? Here's why. We can write it as we can write this as 4x to the -2. And since -2 is not equal to -1, we're going to apply the second rule. Okay? So we can only do the ln rule if it's just x in the denominator. If we have x squared or some other power, it's not going to work. So I'm going to let the 4 float, and then I'm just going to raise the power by 1, so it goes from being -2 to being -1, and I divide by the new power, which is -1. So I get 2 ln absolute value of x minus 4 over x plus c. Okay. This last one, we learned a rule for how to do the antiderivative of e to the kx. Can anybody remind me what is the antiderivative of e to the kx? Sam?
E to the kx over k plus c.
Yeah, very good. E to the kx over k plus c. Perfect. So the 32 is going to float, and I'm just going to leave e to the kx as it is. That's e to the 8x, and I should divide by 8, and then I should add c. So I get 4e to the 8x plus c. Very good. Okay, any questions on these antiderivatives? Okay, there's a great reason that we did antiderivatives as a warm-up today. It's because I'm about to teach you the most amazing fact about calculus that you will ever learn in your life. Okay, I hope that's a big enough lead-in to the fundamental theorem of calculus. Let's talk about it. It says, if f of x is a continuous function on an interval a comma b, and f of x, capital F, is an antiderivative, any antiderivative of f of x. Remember what that means is capital F prime of x is equal to little f of x. Then, okay, have I gotten everything? Continuous function on an interval from a to b, f of x is an antiderivative. Then, the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Okay, so what is this saying? This is saying we can find the area under the curve from a to b by just finding some antiderivative for little f, plugging in b and a and subtracting, and then we're done. We just get the answer. Okay, why is this amazing? I'll explain. It's amazing because before, if we had some crazy function and we wanted to know like the area under the curve from a to b, okay, say we wanted to know this area. Before, we had to do this god-awful process of like taking rectangles and approximating the area and then just using more and more and more rectangles and doing the same thing like 10 times over and hoping that we see a pattern, that this is leading to some number. Now what I'm saying is, if alongside this graph, you also have the graph of, so if this is the graph of f of x, and if you also had the graph of capital F of x, some antiderivative might look different. Actually, it's definitely going to look different. It's going to look something like this maybe. Then what you can do is just find the height of f of x at b and at a and subtract those two heights, and we're done instantly. Okay? So, if you have the brain power to come up with an antiderivative for a function, then we can say all kinds of things about the area underneath the original function just by looking at the antiderivative. Okay? So, let me just really quickly go back to 5.3 and remind you, this is the process that we used previously for computing the area under the curve. We went in, we divided up our interval into n equal size rectangles. We found the height of each rectangle by plugging into the function like 6 times. And then we multiplied all those things by the width of each interval, and then we added them all up, and then we said that, you know what, after all that work, what did we get? An approximation. Yes, Kevin?
But then, like, what do we use for C?
Great question. So let me go to an example. So actually, let me talk about the definition a little bit more. The question you're asking has to do with this word right here, an antiderivative. Any one will do. And here's why. Say instead, so say I had, why don't I make a new page? How about that? I'm really glad that you asked that question, Kevin. So for those of you at home, the question was, what about f of x plus c? Which antiderivative should we use? And are we going to get different answers for different antiderivatives? Well, let's try it. Let's try f of x plus 7 versus f of x minus 2. Now, we want to do the integral from a to b of f of x. It's going to be equal to f of b, let's do the first one first. It'll be f of b plus 7 minus, parentheses, f of a plus 7. And what's going to happen here is you're going to realize that this is equal to capital F of b minus capital F of a plus 7 minus 7. And that's just equal to capital F of b minus capital F of a. And the same thing's going to happen no matter what number we use. If we tried the other one, let's try this one. We'd get integral a to b of f of x dx equals capital F of b minus 2 minus, parentheses, capital F of a minus 2, and we'll get capital F of b minus capital F of a minus 2 plus 2. And that's just equal to capital F of b minus capital F of a. So that's another amazing thing about the fundamental theorem of calculus. We can just pick any antiderivative we want. We don't have to worry anymore about whether it's the antiderivative or an antiderivative. Just pick one, and it'll work. Usually we just pick the most simple one where we just take c, the constant, to be equal to 0. And that's usually the way we go. But if you like adding and subtracting the same number and you get something out of that, then there's no problem with it. Okay, so let's see this in action. I already kind of went back to these notes and tried to show you how inelegant this method is that we were using before. And now you're going to see how amazing this method is on these problems here. So let's try this first problem A here. If we want to find the integral from 0 to 5 of 8x plus 1 dx, the fundamental theorem says, well, just find an antiderivative for 8x plus 1. Then plug in 5 and subtract when you plug in 0. Okay, so let's find an antiderivative. So capital F of x would be equal to 8x squared over 2 plus x plus c. But the fundamental theorem says I should pick any old antiderivative. I'm going to pick the one where c is equal to 0. So I'm going to erase this c here because we don't usually write plus 0. Okay, so that's going to be an antiderivative of 8x plus 1. It's equal to 4x squared plus x. And now what I should do is just plug in 5 and 0 and subtract. So we get integral from 0 to 5 of 8x plus 1 dx equals, let's plug in 5, 4 times 5 squared plus 5, and then we'll subtract when we plug in 0. Well, it'll just be 0. So we get 4 times 25 is 100, plus 5 is 105. Wow, look at that. So last time we spent like 10 minutes on these Riemann sums, which were, at the end of all of our hard work, we accomplished very little. We wound up with an approximation that wasn't even that good. And now we just computed the area underneath this curve relatively simply. Okay? So there's one thing that I want to point out in terms of notation. Let me cut this part. Well, let me cut this part and move it down a little bit. Sometimes what we write here is we'll write the antiderivative, so 4x squared plus x, and then we will write one of these little lines like this, and we'll put 0 and 5 here. So let me just explain what this notation means. This notation means we've taken an antiderivative, and now what we should do is we should take this function, we should plug in 5, and then we should subtract and then plug in 0. Okay, that's what this notation means. So when you see this little bar here, sometimes what I'll say is, okay, 4x squared plus x evaluated at 5 and 0. When I say evaluated at 5 and 0, I mean first plug in 5, then put your minus sign, then plug in 0. Okay, so the top number is the one we plug in first, and then the bottom number is the one we plug in second. All right, any questions so far about the fundamental theorem or about that new notation? All right. Let's do the next one. Okay. Integral from 1 to e of 5 over t dt. Man, that would be a pain to try to estimate using Riemann sums. Because we'd have to split up our interval from 1 to e. We'd have to make a number line with 1 and e on it. 1 and then e, and here's 2 somewhere in here, and 3. And we'd have to take this interval here, this purple thing, and we'd have to split it up into n equal parts, which would have length like e minus 1 over n, and it would just be miserable. It'd be a terrible experience. So instead, let's use this amazing fact we learned about the fundamental theorem of calculus. What should I do if I want to compute this using the fundamental theorem of calculus? What's the first step? Ashlyn? Yeah, first step, find an antiderivative for the function 5 over t. What should it be? Alice?
Should be 5 ln t.
Yeah, it should be 5 ln of absolute value of t. And then we should evaluate that at 1 and e. So what do we get? 5 times ln of e minus 5 times ln of 1. And ln of 1, what's that? What's 5 times ln of 1? Well, if if I have y equals ln of 1, what's the corresponding exponential equation? I should have e to the something equals something. What goes in the power and what goes in on the right hand side? Should it be 1 in the power and y on the right hand side, or should it be y in the power and 1 on the right hand side? Okay, I think people are maybe just nervous to potentially give the wrong answer. Who feels like they actually kind of know what's going on here? Thumbs up if you actually know what I'm talking about. Thumbs down if you're like sort of confused, because I need to know. Okay, I'm seeing some sideways thumbs. The corresponding exponential equation, okay, let me review a little bit then. If we have y equals ln of x, the corresponding exponential equation is e to the y equals x. Okay, we can do that by just taking both sides to the e power, right? If we can put a little intermediate step in here. We can say, okay, e to the y equals e to the ln of x. And you all are smart. You know that e and ln are inverses. So when we do e to the power ln of something, those are going to cancel and we're going to just be left with x. Okay, so that's what's going on here. So if I have y equals ln of 1, the corresponding exponential equation should be what? Kevin?
e to the y equals 1.
Yes, e to the y equals 1. So if we take e to some power and we get 1, what was the power?
0.
Yeah, 0. This means y is 0. Okay. I'm going to put a log and exponential problem on your next exam, so maybe review that, okay? That's super important stuff. All right, so let's see here. So this means e to the y equals 1, so this whole thing here is just 0. ln of 1 is 0. That's a fact that you can either memorize or probably more preferably learn how to do this flip-flop between the exponential equation and the logarithmic equation. Okay, how about ln of e? If I have y equals ln of e, what's the corresponding exponential equation? If we have y equals ln of e, Alice?
E to the y equals e.
Yeah, it should be e to the y equals e. What should y be? Alice? Yeah, it should be 1. E to the y equals e to the 1 means y equals 1. So this is just 1. So the whole thing's just equal to 5. Okay, so maybe that's what we'll spend a little bit of extra time talking about is this logarithm stuff. Okay, I'll have to think about that. For now, we're going to do more integration stuff. So what is the net process? Okay, so if we know how to do ln, then the process is just do the antiderivative. Whoa, that wasn't supposed to happen. This was supposed to happen. Do the antiderivative, and then just plug in e, and then plug in 1 and subtract those two numbers, and then we're done.
Wait, what did you? Oh, sorry.
It's totally possible that I made a mistake. I don't think I did. Right-hand side went to 0. The left-hand side was 5 ln of e. That's just 5 times 1 is 5. Okay, so that gave us the area under 5 over t. What does 5 over t look like? It looks really nasty. It looks like this. And we took the area from 1 to e. And we took this really odd looking shape and we found the area of it by plugging e and 1 into a function which we know how to compute e and 1 with. Okay. So let's see. Any questions about these first two fundamental theorem of calculus problems? You guys like the fundamental theorem of calculus? Cool, me too. I don't like Riemann sums. All right, we'll do this next one. This one should be easier, no ln's involved. 2x squared minus x dx. What do I do first? Yeah, find the antiderivative. What's the antiderivative of 2x squared minus x? Well, what's an antiderivative? Alice?
2/3 x to the third.
Yeah, 2/3 x to the third. And then what about the minus x part?
X squared
Minus x squared
over 2.
over 2. We've got to make sure we divide by that new power. And we're just going to evaluate this at -1 and 1, which means we're going to first plug in the top number, and then we're going to plug in the bottom number, and we're going to subtract those two things. So 2x cubed over 3, when we plug in 1, we're going to get just 2/3 minus 1/2. So that's the first part. That's capital F of B. And then we'll subtract, we'll do capital F of A, the bottom number. So 2/3 times x cubed, that's -2/3. If we plug in -1, because -1 cubed is -1. And then we'll take minus sign, and then we'll have just 1/2. Okay, so this is 4/6 minus 3/6 is 1/6 minus parentheses -4/6 minus 3/6 is -7/6 equals 8/6 equals 4/3. Did I make a mistake? I might have. I don't think I did, but all I did was get a common denominator on each of those. I said, here, why don't I actually write what I did? I multiplied 2/3 times 2/2 to get 4/6. I multiplied this one times 3/3 to get 3/6. And then I subtracted, I did the same thing to this guy. I multiplied the first thing by 2/2 to get -4/6, and I subtracted from that 3/6. So -4 minus 3 got me -7. +4 minus 3 got me 1. Okay, so again, pretty amazing. This is, we could factor this as x times 2x minus 1, which means the roots are going to be at 1/2 and 0. So what does this picture look like? 1/2 and 0. And it opens up, which means that our function looks something like this. And here's 1, and here is -1. So what did we do? We actually took this purple area and we subtracted from the purple area the blue area, the dark blue area. That might look black on the projector. And if we take this purple area and we subtract that blue area, we get 4/3. And it was so easy to do. We didn't have to fool around with any rectangles. We just used the power of the fundamental theorem of calculus. Any questions about that problem? Okay. Let's see here. Maybe we should. Aha, here we go. Now here's a problem with some meat on it. Alright, we should have enough time to do this. All right, find the area bounded between the functions x squared minus 9 and x plus 3. Okay, we learned last time that the area between two functions is just, so this area, this blue area here, it's just going to be the area under the top function minus the area which is under the bottom function. So it's just integral of f of x minus g of x dx. That's how we found the area between curves. But there was a little bit of a snafu. What was the snafu? It was let me redraw this a little bit better. It was that if we wanted to express this as an integral, we had to decide the bounds of integration, a to b. And the bounds of integration, does anybody remember how we found what a and b were going to be? How do we find the points where f of x and g of x cross one another?
Set them equal.
Yeah, we set them equal. So this is where f of a equals g of a. And here is where f of b equals g of b. Okay, so let's draw these two graphs really quick. We'll give it our best shot anyways. So here's -9. X squared minus 9 looks like a parabola opening like this. What does x plus 3 look like? What shape is that? X plus 3. Anyone besides the usuals want to take a crack at it? X plus 3, y equals x plus 3. Yep.
It's a straight line.
Yeah, it's going to be a straight line. Is that the same answer you had, Emily? Okay, good. It's going to be a straight line, and where's the y-intercept? Yeah, positive 3. So here's 3, and it's going to be a straight line with slope 1, just going like this. And our task is to find this area. Kind of a crazy looking shape. But we're not going to worry too much because now we got the big guns. We got the fundamental theorem of calculus. Okay. So, first of all, let's write this area as an integral. It's going to be the integral of, let's not worry about the bounds for a second. What should the function be that we take the integral of? We should have something in here and then dx. My question is, what goes in this blank? Emily?
Is it the x plus 3 minus x squared minus 9?
Yeah, very good. It's going to be x plus 3. That's the top function. And then we're going to subtract from that the bottom function, x squared minus 9. Okay. And now let's concern ourselves with the bounds. What should the bounds be? That's the question. How should I find the bounds? Kevin?
Set the two equal to each other.
Yeah, set the two equations equal to each other. Is that what you were going to say? Okay, same thing. Great. So, we get x plus 3, and we set that equal to x squared minus 9. Okay, let's combine everything onto one side. We'll get x squared minus x minus 9 minus 3, that's minus 12. And that factors as x minus 4 and x plus 3. So this is going to be true at 2 points. It's going to be true when x is equal to negative 3, and it's going to be true when x is equal to positive 4. So what should go here in this bottom bound? Yeah, negative 3. We go from left to right. So negative 3 comes first, and then 4 goes on the top. And now we're ready to actually do this integral here. So we'll just take the integral from negative 3 to 4. Let's clean it up a little bit before we go ahead. Negative x squared plus x, and then 3 minus negative 9 is plus 12 dx. We find the antiderivative. Negative x squared is gonna become negative x cubed divided by 3 plus the x is going to become x squared over 2 plus the 12. What's the 12 going to become? 12x. Evaluate all of that at negative 3 and 4. And our area is equal to negative 4 cubed over 3 plus 4 squared over 2 plus 12 times 4 minus negative 3 cubed over 3 plus 3 squared over 2 plus 12 times 3, negative 3 on all of these. And if you really want, you can multiply all that stuff out and get your final answer. So that's the fundamental theorem of calculus. I hope you're impressed, or at least I hope that you're relieved that you have a much better way of doing things rather than taking Riemann sums. No homework due today. Homework is due next Friday, but it's long, so I suggest you start early. Have a happy Halloween and a safe weekend. Yeah. I have office hours today from 11 to 1.